All right, today we're going to be talking about electricity as a part of the AP Physics 2 curriculum. So we're going to be going over the formulas that are important for the unit, and then we're going to do some practice problems. So the first formula that's important for the unit is Coulomb's law. And Coulomb's law is basically shows the force of the electrical field. And it uses the formula K times Q1 times Q2 over R squared, with K being Coulomb's constant, which is equal to 8.988 times 10 to the ninth Newton meters squared over Coulomb squared. And Q1 and Q2 are charge 1 and charge 2. The charge that you're trying to find the force between, and R is just the radius, or the distance between the two charges. And Coulomb's law, you get a force, so the units for force is in newtons. Then we move on to electrical field, with newtons for which are in newtons over coulombs. So electrical field is equal to the force over the charge, which is equal to K times Q over R squared. And in electrical field, you can see that the lines always leave away from a proton, always enter towards a neutron. Oh, sorry, an electron. So lines begin at the positive end and leave at the negative end. As we can see on this diagram here, the lines are leaving the positive terminal and going to the negative terminal. And then we talk about potential energy, the units for which are joules. And potential energy is measured as change in potential energy is equal to K times Q1, Q2 over R, with K being Coulomb's constant, which is equal to, once again, 8.988 times 10 to the negative, sorry, 10 to the positive 9. And Q1 is charge 1, and Q2 is charge 2, with R being the distance between the two charges. And then electrical potential difference, which the units for which are V, which is volts, is electrical potential difference is equal to the change in the potential energy over Q. So the formula is KQ over R. Now, when we talk about capacitance, there's a couple of formulas for it. So capacitance is equal to K times the permittivity of free space times the area cross-sectional area of one of the plates over D. So K is the dielectric constant of the material. So if we have a dielectric constant between two plates and a capacitor, the capacitance will actually increase. But if we don't, then we can just remove it from the formula, and the formula will just be K times EO times A over D. If we do, it's a material that's placed in between the two plates in the capacitor, increasing the capacitance. And the units for capacitance are F, which is farads. And then capacitance also measured as Q over V, which is charge over the electrical potential difference. And then there's two things for in capacitance. So you can have in series, the elements will have the capacitors will have the same charge, and the equivalent capacitance is calculated as then 1 over capacitance 1 plus 1 over capacitance 2, the sum of all these capacitances raised to the power of negative 1. But if you're in parallel instead, it'll be the same voltage across all the capacitors, and the equivalent capacitance is just calculated by multiplying all the capacitors together. Sorry, adding all the capacitors together. The way electrical current is measured in amperes, so the units would be A. And then electrical current is equal to the change in charge over the change in time. So electrical current is the rate at which charge flows through a given cross-sectional area. And another formula for finding electrical current is I is equal to NQVD times A, with N being the number of charge carriers per unit volume, Q being the charge on one of the carriers, A being the cross-sectional area, and VD being the drift speed. Now, if we're talking about resistance, so resistance is equal to V over I, and the units of resistance are ohms. And then resistance is also equal to rho L over A, with rho being the resistivity of the material, L being the length of the material, and A being the cross-sectional area of that. Now, if you find the power of a circuit, we can find it in multiple ways, with power being equal to I times V, which is the charge times the voltage, or I squared times R, which is the charge over the charge squared times the resistance, or V squared over R, which is equal to the electrical potential difference squared over the resistance, the circuit. And power is measured in watts, so the units would be W. Now, if we're trying to find electromotive force or EMF, it's equal to the in order to calculate EMF, you would have to find the electrical potential difference and then add that by the internal resistance, and then you would get E or EMF. With R being the internal resistance, and you calculate internal resistance by multiplying the charge times the resistance of the internal circuit. And now if we have resistors in series, we do the equivalent resistance would be equal to the sum of all the resistors in the series. And once again, this would be in ohms because that's a unit for resistors. But if we instead were in parallel, the equivalent resistance will be 1 over resistance 1 times 1 over resistance 2. Sorry, 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3. So 1 over the sum of all the resistors raised to the power of negative 1. Once again, in ohms, because that's a unit for resistance. Now, for junction rule is basically conservation of charge, and it states that the charges going into a junction or a node must equal the charges going out of that junction or node. Now, if we have loop rule, it's a conservation of energy, and it basically states that the equivalent potential energy, conservation of energy, and basically states that the what the fuck? I didn't do this. I didn't do that. So if we have loop rule, it's conservation of energy, and it states that the electrical potential difference going into a closed loop must equal zero. If we're talking about RC circuits, one of the formulas is T is equal, tau is equal to RC, the tau being the time constant that has units of S seconds. And if we're charging a capacitor, the formula is equal to the charge is equal to the max charge times 1 minus e to the power of negative t over tau. And if we're discharging a capacitor, it would be charge is equal to the initial charge times e to the power of negative time over tau. And for circuits, as is stated for the resistivity formula, which is equal to 1 over V over I. So V over I, sorry. So for circuits, the formula which we stated originally for resistors was R is equal to electrical potential difference over the charge. This formula can be rearranged to the electrical potential difference is equal to the charge times the resistor. And this formula can also be arranged to the charge is equal to electrical potential difference over the resistivity or the resistance. And those are all the formulas for this unit. I'll move on to some practice problems.
Now, this first question is a multiple choice question. The figure represents a section of a circuit containing three capacitors, X, Y, and Z. Among them, X and Y have the same plate area, but X has double the plate separation. Y and Z have the same plate separation, but Z has half the plate area. Rank the plate's charges in the correct order of magnitude. Now, for this problem, the main focused formula that you use to solve it is this one, where the charge of the capacitor is the K constant times the electricity constant over the area divided by the plate separation. I split up the problem into three of the different capacitors, and for X, the question states that X has double the plate separation, so you multiply the separation here by 2. For Y, it says that it has the same plate area as X and the same plate separation as Z. So you leave nothing, you just leave that as is. For Z, it says that it has half the plate area as Y. So then you put the 1/2 here, and if you were to compute these equations out with numbers, imaginary numbers, or if you just plug in the equation as is with the 1/2 and the 2, you get that X is equal to Z, and they're both less than Y. So let me rewrite this here. Since nothing is changed in the Y formula, the distance is not multiplied by 2, the entire equation is equal to the biggest out of all the three, so Y is the greatest. With X, since you double the plate separation, you have a 2 in the denominator, which halves the entire equation. And with Z, you want half the denominator, which ultimately means you're halving the entire equation. So that makes these two equal, but that makes the X and the Z equal, but still less than the Y. So this is the answer.
So let's do this question right here. A 60 nanocoulomb charge is located at x equal to 0 meters on the x-axis, and a 90 charge is located at x equal to 3 meters. So part A, what is the electric field at x is equal to 5 meters? So first, let's draw the line here for our charges. So right here, we'll have x equal to 0, so we'll have our 60 nanocoulomb charge. And then right here, we'll have our 90 nanocoulomb charge. And both of them are positive, so they're like that. And then over here, we have 5 meters. So what is the electric field at x equal to 5 meters? So electric field is going to be equal to the electric field at 0 meters plus the electric field at 3 meters. So that will equal to KQ1 over R1 squared plus KQ2 over R2 squared. And that will become, you can take out the K, it's just a constant. So 60 times 10 to the negative 9 is to convert it. That's over 5 meters or 5 squared because this to this is 5 meters. And you add that to 90 times 10 to the negative 9 over 2 squared because 3 meters to 5 meters will only be 2 meters. And doing so, you get the electric field at 5 meters is equal to 223.85 Newtons over coulombs. And this will be away from the charges. And the reason for that is because if you have a positive charge like this, it pushes away from itself, like that. So that means these positive charges right here, they'll be pushing away like this, like this, like this, like this. So at this point right here, so at this point right here at 5 meters, both of them will be pushing away like that. So it'll be pushing away like this. So therefore, at 5 meters, both charges will be pushing like that. So it's away from the charges. So that will be our answer for part A. And part B asks at what point on the or points on the x-axis is the electric field 0. So to do this, we have to pretty much um, equate both electric fields. And doing so, we get 60 times 10 to the negative 9 over, this will just be r minus 0 squared. Because if we have, like, for example, if our value is something like 2, for example, then r would be 2 minus 0, and that is the distance from here to here. That's equal to 90 times 10 to the negative 9 over 3 minus r squared. So if we have the same example, for example, 2, and we have 3, then 3 minus 2 is going to be 1, and that is indeed the distance between these two. So solving this for r, because it's a quadratic, we get two things. We get 1.348 meters and negative 13.348 meters. So 1.348 meters makes sense because it's around over here, right? So this is pushing this way, this is pushing this way, so it makes sense that it would be zero in between this area. However, negative 13.3848 meters does not make sense because that would be somewhere over here, right? So we'd have this pushing this way and this pushing this way. So if it's like this, it's the same thing with 5 meters. They'll simply just add together to make a larger electric field. So therefore, that negative 13.348 meters is not one of the answer choices. Therefore, it's only 1.348 meters. So that's the question. So let's try this practice problem. A 47 ohm, 33 ohm, and 15 ohm resistor are connected in parallel to an EMF source. A current of 0.3620 amps is in the 33 ohm resistor. So part A, calculate the equivalent resistance. So to find the equivalent resistance of a parallel circuit, we have to do the sum of the inverses. So the equivalent resistance will look like this. So this will equal to, so R47, the resistor is 47, obviously this should be 47, this would be 33, and this would be 15. So doing that, you get the equivalent resistance to be 8.457 ohms. So that's your equivalent resistance. So part B. Part B asks to calculate the current in the other resistors. So we get the current in the 33 ohm resistor. So let's use that. So V is equal to IR. So I, the 33 ohm resistor, and resistance the 33 ohm resistor. So V is equal to I, which will be 0.3620 times resistance, which is 33 ohms. So we get the voltage of this one to be 11.946 volts. And keep in mind, in a parallel circuit, the voltage stays constant. So we can use this voltage everywhere to find the voltage or to find the current in the other resistors. So voltage is equal to I of, let's do the 47 ohm resistor. So voltage will be equal to I 47, what we're trying to find, and then this would be 44 ohms. And obviously we can use the voltage as 11.946. So we get I 47 to equal 0.254 amps. So now for the final resistor, which is 15 ohms. So we can use the same voltage. That's equal to 15 times resistor, resistance of the 15 ohm resistor is 15. So we get I, the current of the 15 ohm resistor is 0.794 amps. So that's that. Now let's do part C over here. So for part C, we just have to draw a diagram or the schematic. So we'll draw it like this. Have our one resistor there, second resistor there, and our third resistor there. And then we'll have the battery. We can label it too. So this will be our battery, which we know is 11.946 volts. This will be 47 ohms, 33 ohms, and finally 15 ohms. So now for part D, we have to find total power dissipated in the circuit. So power is equal to V squared over the equivalent resistance. So V squared is obviously going to be the voltage squared. And because our voltage is constant, we can use this the voltage that we found in part C. So 11.946 squared over the equivalent voltage or equivalent resistance, which we found in part A, which is 8.457. So now that equals to 16.87 watts. So that's this entire problem done.